This is video 9.2, Simplifying Square Roots. Let's start by learning a little bit about the vocabulary. This is a radical sign, and it's used for finding square roots. So for instance, if I have the square root of 9, I'm looking for what squared would equal 9. Well, 3 times 3 is 9, so 3 is the square root of 9. It could also be negative 3, because negative 3 times negative 3 also equals 9. So all of these equal 9. So the square root would be 3. Now let's think about this. If I have x squared, the inverse operation of squaring x is to find the square root. So if I find the square root of x squared, I have x. Now let's look at two important principles. One is what we call the product principle of square roots. So let's imagine that we have the square root of 4, and it's being multiplied by the square root of 16. Now if you look at this principle, the square root of x times y equals the square root of x times the square root of y. This is where x is greater than or equal to 0 and y is greater than or equal to 0. So that means x or y cannot be a negative integer. So let's look at our two numbers here. If this is true, then I should be able to rewrite this as the square root of 4 times 16. Now I know that 4 times 16 is 64. And I also know that 8 squared is 64, so 8 would be the square root of 64. So this would be an application of the product principle for square roots. Let's look at another example. Let's say I have the square root of 9 times 7. All right? This is the same as the square root of 9 times the square root of 7. Now what's nice about being able to split these up is it means I can simplify it. I can find the square root of 9, which is 3. There is no way to simplify the square root of 7, so I end up with a simplified version, 3 to the square root of 7. So using the product principle of square roots helps us simplify square roots. The second principle we're going to learn about is called the quotient property of square roots. This is where x over y, the square root of x over y, or divided by y, equals the square root of x divided by the square root of y. This is where x is greater than or equal to 0 and y is greater than 0. Notice y can't be 0 because we can't divide a number by 0. So let's look at an example. Let's say that I have the square root of 11 over 4. Now I can also write this as the square root of 11 over the square root of 4. Now I can't simplify 11, square root of 11, but I can simplify the square root of 4. So this will give me the square root of 11 over 2, because the square root of 4 is 2. So this would be a simplified version of the original expression. All right, let's apply this further. Let's say we're trying to simplify the square root of 176. All right, let's find what some of the factors of 176 are. Well, I know that I can multiply 16 times 11 and I get 176. Now notice that I specifically tried to pick a number that goes into 176 that is a square number. All right, now that I've done this, I can separate it out and get the square root of 16 times the square root of 11. So I've now used the product principle of square roots. I can simplify this one to 4, but I can't simplify the square root of 11, so it's 4 to the square root of 11, and that would be my answer, simplified. Let's look at another example. Right, this one is the square root of 432 times y squared. So let's break this one apart. Let's say that I have the square root of 4 times 108 times y squared. Alright, let's see if we can even factor this out further. I can factor out 108 to 3 times 36. So now I've got 4 times 3 times 36 times y squared. Alright, I can rewrite this as the square root of 4 times the square root of 3 times the square root of 36 times y squared. I know the square root of 4 is 2 times the square root of 3 I can't simplify. I know the square root of 36 is 6. And I know the square root of y squared would be y. Alright, now I can multiply these like terms, and I get 12y to the square root of 3. And that would be my answer simplified. So first, I factored out my 432. I separated them out into separate square roots. I solved the square roots that could be simplified, and I did the multiplication. Now let's look at a quotient principle, square root. For this one, I have the square root of 202 over 256. Again, I can rewrite this as the square root of 202 over the square root of 256. Now let's try to factor these out. The square root of 202 I could factor out as 2 times 101. Now you'll notice that these are prime. It means they can't be factored out any further, and that neither of them have a perfect square. So 202 is just going to have to say the square root of 202. I can't simplify this. But I know that 256 is the square root of 16 times 16, or just 16. So I can rewrite my expression as 2 over 2 over 16. So I've got the square root of 202 over 16, and this would be the simplified version of this expression. Right? Let's try a story problem. A square has an area of 700 square units. Find the length of the side of the square as a radical expression in simplest form. Alright, well, if I have my square, and I know that my square has a side length of 700 units, sorry about that, has an area of 700 units, and I'm trying to find out what my side length is. Right? Well, I know that my side times my side will give me 700, so I'm looking for the square root of 700, and I need to simplify this. Okay, I'm going to start by factoring it out. I know that I can factor 700 as 2 times 350. And I know I can further simplify it as 2 times 175. So now I have 2 times 2 times 175, which when multiplied all equals 700. Here I can multiply 5 times 35 to get 175, and I can multiply 5 times 7 to get 35. So in the end, when I take 700 and it's completely factored out, I end up with 2 times 2 times 5 times 5 times 7. And these are the prime factors of 700. Right? Now, I know that 2 2's, or 2 squared, is the inverse of the square root. So that means that I can take a 2 out. So it's like I have the square root of 2 squared times the square root of 5 squared times the square root of 7. And so this is 2 times 5 times the square root of 7, or 10 times the square root of 7 would be the side, or units, would be the side length of my square. And that's simplified. Now, let's make it a little bit complicated by adding more variables. All right? For this particular square root, I have 152 times m squared times n. Now, I can factor out 152. 2 times 76, 2 times 38, and 2 times 19. So now if I rewrite this, I have the square root of 2 times 2 times 2 times 19 times m squared times n. I'm going to look for pairs. I can rewrite this as 2 squared to the square root times the square root of 2 times the square root of 19 times the square root of m squared times the square root of n. Now, which of those can I find the square root of? Well, this would be 2, because these are inverse operations. I can't simplify this one, so I'm left with the square root of 2 times the square root of 19. This simplifies to m, and this has to stay the square root of n. Right? I have these two, so I get 2m times the square root, and again I could put these back together, 2 times 19 times n, or 2m to the square root of 38n. And this would be this expression simplified, or that square root simplified. All right? All right, let's do one more. Again, this is a quotient. So I'm going to convert this to the square root of 76 p squared q squared over the square root of 81. Now, this one's going to be a lot easier because I know the square root of 81 is 9, because 9 squared is 81. So, on the bottom, I know I've got a 9. On the top, I need to factor this out. All right? So, if I take the square root of 76 p squared q squared, 76 can be factored into 2 times 28, or 38, and then 2 times 19. So I'm left with 2 times 2 times 19 times p squared times q squared. So I'm finding the square root of this on top of my quotient. All right, 2 times 2 leaves me with a 2. 19 can't be factored out. P squared, the square root of p squared would be p. So I can take my p out and my q can come out. So I end up with 2pq to the square root of 19. So that would be, goes on top. Now there are a few problems for you to try. And this is the end of video 9.2, Simplifying Square Roots.